Ciba Geigy, research scientists create products which enrich the quality of our lives. Products to increase our food supply, dyes and pigments which surround us with color, pharmaceuticals to improve our health, products which reaffirm the value of science to mankind. As part of its continuing program in support of science education, Ciba Geigy is pleased to present this issue of the Science Screen Report.
The Science Screen Report. Developments in science, engineering, and medicine that help solve the problems of modern life. Almost all objects in everyday life, clothing, food, cars, homes, involve hazardous materials in their production. Making a TV, circuit boards etched with hydrofluoric acid. Manufacturing a car, several hazardous chemicals and wastes. About 150 kilograms of hazardous materials are created per person every year. This is a report on efforts by science and engineering to solve the problems of hazardous materials, ignitable, corrosive, reactive, or toxic substances. These are hazardous chemical wastes, improperly disposed of. Once in the soil, one response to the problem is to dig trenches around the dump to allow collection of any hazardous materials which may seep out. The material can then be drawn off and treated separately. New laws now govern cleanup of such sites. A more complex, serious issue is making certain today's hazardous materials don't cause problems tomorrow. As the following examples suggest, each hazardous waste problem requires its own total management program. At a Rhode Island chemical plant, 6,000 kilograms of zinc, hazardous in high concentrations, is used daily in production of pharmaceuticals. In this case, recovery and reuse of zinc wastes was found safe and cost-effective, part of the New England Regional Hazardous Wastes Management Program. California's electronics industry wastes are recorded on tracking forms, including amounts, concentrations, and disposal systems, part of a state management program now required nationwide. The materials are then transported via licensed haulers using special trucks to approved disposal sites. On site, samples are drawn and analyzed to double-check toxic characteristics. A treatment plan is set up for those specific wastes, in this case involving clay-lined solar evaporation ponds. After 7 to 10 years, ponds are dried and bottom solids, waste components still defined as hazardous by law, deposited in sealed, monitored landfills. In Texas, a state plan deals with all hazardous wastes. This petrochemical complex makes industrial resins, chemicals for food containers, car paint, and hundreds of other uses. Resulting hazardous wastes take the form of organic gases, liquids, and solids. Organic liquids delivered in tank cars are stored, blended with other materials, and incinerated. Semi-solid materials are placed in fiber packs, loaded into rotary kilns, and incinerated. Solids go into a chemically sealed landfill, a container whose bottom, sides, and top are chemically secure barriers. Such landfills are monitored via sampling wells, from which nearby soil samples are periodically drawn for testing. State law requires recording of all such sites, followed by monitoring for 20 years. The following film sequences represent systematic procedures employed by the chemical industry for safe, ongoing management of toxic materials. As the first step, any substances to be added to the environment, flame retardant, food additive, pesticide, and their byproducts and waste products are laboratory tested to determine possible health hazards. Tests begin with direct exposure of living cells in petri dishes to the new substance. The criteria: mutagenicity, carcinogenicity, toxicity. That is, will the new substance affect living cells so that they mutate, become cancerous, or die? Test materials are also mixed into food and fed to experimental animals. The question: is there a threshold level for effects in food? Exposure also results from inhalation, breathing in chemicals. These inhalation chambers simulate such exposure for given time periods and concentrations. Subsequent studies of test animal tissue determine possible cell damage. A test sequence may take many years and cost millions of dollars for a single new substance. The goal? To ensure that the new substance causes no harm, either by making certain it is safe or by learning how to best manage it. The production site must also be made safe. At this ethylene plant, among other safeguards, an air quality flare consumes waste hydrocarbons, converting them to carbon dioxide and water. The flare is continuously monitored from a control room, which also keeps track of other safety systems. Work areas are likewise monitored. Protective programs include ongoing health histories for each worker and periodic medical examinations. Exposure to any harmful substance is detected via personal air pollutant monitors, calibrated, miniaturized air sampling pumps which operate continuously. Air drawn through a filter is analyzed to determine exposure for the day. The goal? Employee protection through ongoing medical surveillance. Delivery of hazardous materials is also monitored by the manufacturer until the substances reach their destination. For some cargoes, special cars designed specifically to survive derailment intact are used. Routing is done by shippers working with manufacturers, so to, if possible, bypass densely populated areas. Before loading, an inbound inspection detects possible container problems. An inspection repeated in the loading area. Checks include both wheels and running gear, as well as all tank valves and fittings. Loading, the right materials in the right carriers, is followed by an outbound inspection and a final check at pickup by the carrier. 4 inspections in all. From then on, the manufacturer continuously tracks his cargo to destination. If there's a delay or other problem, he carries out rerouting or another previously planned response. Today, the industry has a comprehensive system for managing any hazardous material. Contaminated water can be processed to alter acidity, remove suspended solids, or deal with oxygen-consuming materials before discharge. The liquid is monitored throughout treatment and the river after treatment, ensuring quality standards. Other wastes may be incinerated, a process with several stages. First, combustion via natural gas, yielding carbon dioxide and water. Next, possible recycling and reuse of some waste components. Finally, an irreducible minimum of solid wastes, ash and others, some hazardous, to be disposed of. A secure hazardous waste landfill should protect nearby underground water supplies. A layer of compacted clay is added to any natural clay present. The goal? Sufficient compacted clay so to adequately seal off wastes from groundwater, creating an impervious clay container. When the landfill is full, it is then sealed, compacted clay placed atop it, then topsoil, which is reseeded. Monitoring wells encircle the site, reaching down into the groundwater, whose impurity levels are regularly recorded. Regular sampling reveals changes in those levels, and so any materials moving off-site. Because groundwater moves slowly, any such escaping wastes can be extracted by interception systems. Technology, of course, is only as good as the people who operate it. And today's chemical industry workers are aware of their legal and moral responsibilities. Hazardous wastes are generated in making most manufactured goods, growing and protecting foods, purifying water, producing medicines, and other industries which contribute to our way of life. Effective methods now exist for comprehensive, safe, efficient management of those hazardous materials, from generation to transport to final disposal. Moreover, current answers are the basis for ongoing research efforts aimed at further improvements.
Science Screen Report has been presented by Ciba-Geigey's McIntosh, Alabama plant, producers of over 100 industrial and agricultural chemicals, as part of its continuing program in support of science education.